Hello and welcome back to my channel about sound processing and electronics. In the previous series I discussed the internal structure of the distortion effect pedals. The one active element in this series was an operational amplifier. A stage based on this element has simple engineering calculation because for our purposes op-amps have a nearly ideal characteristics. For example, infinity open loop gain and infinity input impedance. But for many applications, op-amps are redundant, and for others they have unsatisfying characteristics, for example noise-to-signal ratio and so on. In this series I present a new component that has perfect application potential for analog audio. Meets the junction field effect transistor, also known as the JFET. This device is a little simpler in application than the commonly used bipolar transistor, but it has its own features that provide its unique place in the family of amplification devices. For us, a discrete JFET transistor represents a little black box with 3 pins. These 3 pins are named gate, source and drain. To understand what's going on, I want to start the explanation from the physical processes in the JFET transistor. In the illustration we see a box with 3 terminals. The first terminal is connected to p-type semiconductor, the other 2 to n-type semiconductor. If you don't know what p-type and n-type silicon are, you can think about p-type as a material with free charge particles, but opposite to electrons, positively charged. N-type silicon has free electrons with negative charge. These semiconductor areas are separated by a thin depletion layer that doesn't have charge carriers. This is the first feature of the JFET transistor. The depletion layer provides a very high resistance between the gate and the other terminals, and for our purposes we take it as infinity. Before we consider the processes in the transistor, let's first define the parameters for our 3-legged device. Currents and voltage must represent all possible combination of the transistor pins. For simplicity, first consider the currents. At one node 3 wires cross, which means we have 3 currents. ID – currents into the drain terminal, IS – current to the source terminal, and Ig current into the gate terminal. Kirchhoff currents law for the 3 terminals show that the sum of these currents must be 0. Above we stated that the depletion layer has practically infinity resistance. This means that the gate has a negligibly small current, ID equal negative IS. As for voltage, we must consider the pairs of pins. There are 3 voltage parameters for JFETs. We describe voltage between terminals, always with polarity, first terminal minus second terminal. VGS – gate to source voltage, VDS – drain to source voltage, and VGD – gate to drain voltage. Now we are ready to dive deeper into the processes in the transistor. From a practical point of view, the JFET transistor is a device that can control drain current via gate-to-source voltage. The amplification of a signal is based on this property. If we change the gate-to-source voltage according to the signal form, the drain current flowing through the resistor and the drain source path causes a voltage drop that can be significantly larger than the input voltage. To illustrate this, look at the analogy on the image. The drain source path is shown as a tube with a flexible rubber coupling inside. The drain current ID is represented as a water flow through this tube. The gate voltage VGS plays the role of gate pressure that squeezes the rubber wall. When the pressure increases, the passage narrows and the flow decreases. When the pressure is released, the passage widens and flow increases. In this way, the small signal applied to the gate controls the large drain flow, giving the principle of amplification. How does the JFET provide this important effect? Consider what's going on in the shown semiconductor structure. If we apply voltage to the drain and source and the gate is grounded, charge can flow through the region between the gate areas named a channel. In our case, this is electrons, and we have n-type channel JFET. There are p-type FETs, where the channel has Hall conductivity. If we put a voltage supply between the gate and source, it changes VGS from 0 to a negative voltage supply value. The electrons from the channel start to avoid the p-junction area and the depletion region spreads wider. This reduces the channel and the current through it. As a result, we can regulate current flow by VGS. To make it more clear, look at the other illustration. The channel is shown as a tunnel where electrons are moving upward from source to drain. The gate regions act like walls that can expand into the channel. When VGS equals 0, the tunnel is wide, and many electrons can move through. When a negative gate source voltage is applied, the walls push deeper inside, squeezing the flow of electrons. The tunnel becomes narrow, and only a few electrons can pass. In this way, a small signal applied to the gate voltage controls the much larger electron flow in the channel. But why, when I applied drain source voltage, did the depletion region deform? How does changing VDS affect the channel? Return to the previous illustration with grounded gate and source. When current flows through the channel, it may be represented as many spreaded resistors with partial voltage drop on each of them. Therefore, electrical potential in the channel has a gradient distribution. Therefore, the voltage between the top of the channel and gate will be larger than between the bottom of the channel and gate. This explains why the depletion region is deformed. But what's going on when we change the drain to source voltage from 0 to a certain value with constant VGS? Consider the IV diagram for these processes. On the illustration we can see how the IV curve corresponds to the physical channel. The orange dot on the graph shows the working point. On the right side, the channel drawing explains what's happening inside the transistor at this point. At VDS equals 0, we obviously have no current. If we slowly add voltage, the depletion regions start to grow because unevenness of electric potential leads to this, as shown above. At a certain moment, when we reach a certain voltage point, the channel can be narrowed more. At this point, further increase of VDS does not affect the current through the channel. This is named saturation. The drain source saturation current at VGS equals 0 has a special sign, IDSS, and plays an important role in the mathematical description of the JFET. If we change VGS from 0, we obtain a family of IV curves that are placed below the previous one. With each step to more negative VGS, the current level to the saturation region decreases. At some point, when reaches a certain critical negative value, the channel closes completely and no current can flow despite the applied drain to source voltage. This gate source voltage is called the pinch-off voltage, denoted as Vp. It is the second crucial parameter for the JFET together with IDSS. The plot shows how the drain current ID depends on VGS at fixed drain to source voltage. When VGS equals 0, the current is maximum and equal to IDSS. As we make VGS more negative, the drain currents decreases smoothly until the VGS equals pinch-off voltage, it becomes practically 0. From the physical point of view, pinch-off happens because the depletion region from the p-n junction on both sides of the channel expands so far into the n-type material that they meet in the middle. At this moment, the conductive path is fully blocked. Electrons from the source cannot reach the drain and the transistor behaves as an open switch. My description has significant disadvantages. To understand that, we can play with an interactive graph that represents the dependencies of values in the transistor operation. Set the gate source and drain source voltage to 0. In the representation of the transistor, we can observe a colorful channel. Color represents the electric potential at each point. If we slightly change VDS from 0 to 1 volt, we can stay in the region where drain current changes significantly with VDS. When VDS reaches 4 volts, the channel has minimal width and the point moves to the saturation region. In our ideal case, further increase of VDS should not affect the current, but in reality there is still a little influence. This effect is expected in the slope of the curve. If we divide delta I by delta V, which represents the slope of a line in this region, we obtain the differential resistance of the channel in this regime. In the ideal case, we must have infinity differential resistance in saturation, but we have a finite value which is denoted as Rd. The interesting part is that the resistance depends on VGS, and for another curve with voltage, for example, equal to half of the pinch-off voltage, the saturated region of the curve has less slope than the for zero VGS. This change of slope introduced nonlinear distortion of a signal in JFET-based amplification stages. On the diagram we can see this effect as the difference between the ideal load line and the real load line. In the ideal case, the line would cross all the IV curves symmetrically, and the amplification of a sine wave would also be symmetrical. The positive and negative halves of the waveform would be stretched equally. But in reality, because the slope of the curve changes with VGS, the real load line bends and shifts. The small signal model is used for cases like ours. We have heavily nonlinear dependencies in our device, but for analytical calculation we need a linear approximation of this device. That approximation allows us to represent the transistor as a tricky circuit consisting of linear elements such as a resistor, currents or voltage sources, and other linear components. In physics, this approach is called linearization and gives differential ratios for nonlinear models. We are interested in how small variation of input voltage around the chosen operation point change the currents. This point is also called the Q point or bias point, and it is chosen inside the saturation region of the transistor, where the device can act like a stable amplifier. On the diagram we see two main regions of JFET operation, the ohmic region on the left and the saturation region on the right. In the ohmic region the device behaves like a voltage-controlled resistor, and the current changes linearly with VDS. In contrast, in the saturation region the current depends mostly on VGS and is nearly independent of VDS. For amplifier design we choose the operation point in this saturation region, because it allows the output current to follow the gate voltage variation with good stability. We know that the JFET is a nonlinear device, because the drain current depends on both gate source voltage and drain source voltage in a complicated way. But if we choose Q point, we can look at how small variation around this point change the current. Mathematically, the drain current is a function of two variables. If we apply small changes delta VGS and delta VDS around the operation point, the corresponding change in current can be written as a total differential. Here appear the two most important small signal parameters. Transconductance, denoted as Gm. This shows how sensitive the drain current to the change in the gate source voltage. And output conductance, GDS. This shows how sensitive the drain current to the changes in the drain source voltage. This parameter is the reciprocal of the differential drain resistance. This mathematical representation allows us to replace a nonlinear transistor with an equivalent small signal circuit made of dependent current source in parallel with resistor. It is this linearized form that we will use to calculate gain, resistance and frequency response in amplifier analysis. This circuit will be explained in detail in the next video. On the screen we can see the ohmic region highlighted in blue on IV curves. The steeper the slope of the curve, the lower the channel resistance. As VGMs becomes more negative, the slope decreases, meaning the channel resistance increases. This visualizes directly how the gate voltage changes the effective resistance of the JFET channel. For the ohmic region, the general expression is as follows. For very small VDS, we can ignore the quadratic term and simplify expression. From this formula, we can derive the resistance of the channel. JFET as voltage-controlled resistor has audio applications. For example, it used for building voltage-controlled amplifiers, as often used in JFET compressors. The Shockley model describes the JFET in the saturation region. With channel length modulation included, the drain current is as follows, where lambda is channel length modulation factor that models the small positive slope in the saturation region. Setting lambda equals 0 gives the ideal Shockley law. This means we can determine the drain current only by two parameters and one variable, VGS. If we return to small parameters, we can derive transconductance from the Shockley equation. Differentiate expression for drain current with respect to VGS, we take next expression for transconductance. At gate source voltage equals 0, we get the maximum transconductance. Solving the Shockley law for VGS and substituting gives the widely used current-based form. The output conductance arises from channel length modulation. We can derive it in the same way. From measurement, you can read the slope of the IV curve at the bias point and get drain resistance and estimate lambda. Typical small-signal JFET stages biased on the saturation have drain resistance from 10 kΩ to megaohm, which is why the saturation lines look almost horizontal but not perfectly flat. Thanks for watching. Today we met the JFET, so how gate source voltage controls the channel, and draw the core equations. Next time we will consider an equivalent scheme of the JFET and build a real common source amplifier. Further, we modify it into treble booster. You can leave questions in comment, I will read all comments.